Hello, welcome to Lecture 8, Part 2 for Life in the Universe. Continuing in Unit C, where we're taking a look at aspects of life on Earth to try and get some feeling for how it might look in general. And this part is going to be about the importance of water. In other words, talking about the fact that any complex chemical system, such as a living organism, is going to need some type of liquid solvent to let those chemicals be able to move around, interact with each other, and so forth. And for all life on Earth, that solvent is liquid water. And this is an encouraging sign in one way for life because water is a very common molecule cosmically. Because look what water is made of, H2O, okay? Hydrogen is the most common element in the universe. Helium is the second most common element, but helium doesn't like making molecules. Oxygen is the third most common. So there are a lot of H2O molecules in the universe. The problem is most of that H2O is not liquid. It's either solid or gaseous. But right away, this is where we get the idea of a promising place to look for life is look where there's liquid water. Now, there are some alternatives we might think of that also might serve the place of water um, that could work as a solvent for some other type of biochemistry. But water has it seems, a number of advantages over those. And one of those is that water is liquid over a pretty large range of temperatures compared to some other candidates. And importantly, at warmer temperatures. That's what it means by biologically useful. Chemical reactions take place faster when it's warmer. And so it doesn't mean one of these others where that are liquid at colder ranges of temperatures wouldn't work, but any organisms using them would probably have relatively slow metabolisms. So this is basically a little plot for water and a few of the proposed alternatives showing the range of temperatures at which they are liquid at a pressure of 1 atmosphere, so surface pressure on Earth. The pressure under which a material is under actually makes a big difference as to whether or not it's a liquid or a gas, somewhat less important for where it's a solid. So you have to take that into mind. But just for comparison, we'll just use this 1 atmosphere pressure. And so we know we've got a full 100 degrees Celsius range for water, okay, from 0 to 100 degrees Celsius. Okay, for these others, NH3, that's ammonia. Ammonia has was about 45 degrees Celsius range over which it would be liquid from negative 78 to negative 33. It's a difference of 45. So that's less than half the range of water. Methane is liquid under only an 18-degree range at 1 atmosphere pressure. Ethane is pretty good. That's about a 94-degree range, although much colder temperatures than for water. And the thing is, the more complex your molecule gets, the less of it there is. So that is potentially more of a problem. So it seems right here we've got one reason why water might in general be better, although this wouldn't rule out the others. Just very different environments. But then there are also some other properties of water, some of which are related to the fact that water molecules are very much polar, which are helpful. And I'll mention a couple of them. You can look up more if you're interested. So this is a little cartoon view of the water molecule, which you see are water molecules look just like Mickey Mouse's head, where the ears are the hydrogen atoms and the rest of the head is the oxygen atom. Now, even though the molecule is electrically neutral overall, the electrons that normally would belong to the hydrogen atoms tend to spend more time down around the oxygen atom. And that means this end of the molecule effectively is slightly negative, and the hydrogen molecules, Mickey's ears, are therefore effectively positive, even if the molecule as a whole is electrically neutral. And so that means the hydrogen atom in one molecule can attract the oxygen atom in another, because remember, opposite charges attract, and you can form these bonds between water molecules that we call hydrogen bonds, because they arise because of this uneven distribution of charge because of what the hydrogen atoms' electrons are doing. Um, the details of how the molecules of water kind of put themselves together give it one of its particularly unusual properties, because most materials just kind of straight off, as they get colder, the molecules get closer together, they get denser. And it turns out, however, that cold liquid water is denser, however, than solid ice, solid water ice. In a liquid, you have bonds between molecules that are continuously breaking and reforming, and that's what lets water do things, or liquids do things like, let me get out of the share, let my beverage show you here. This is what lets liquids flow easily. So if I tilt it over, the shape of the beverage in my bottle changes. But because there are bonds between the molecules in my beverage, I can take the lid off of it like that, and then this room is now not full of Diet Pepsi, because unlike a gas where there are no bonds between the molecules, liquids can't then just spread out to fill whatever volume you give them. Take advantage of that for a drink. Now I'll use, let's see here, I'll just use this, that's kind of flexible. What do I have here that would be better? Oh, well, what about this? Oh, okay, we'll use this. Okay, some nail clippers here made out of some kind of metal. Okay, in a solid like these nail clippers, then the molecules are all fixed in position relative to each other, because the bonds are strong enough to where it would take quite a lot of effort to break them. And that's why solids have, this is why the shape of the nail clipper doesn't change significantly as I tilt it to different orientations. All right, let's see here, back to sharing. Okay, now, so like I said, it turns out that for water, just because of the details of those interactions, as cold water, the molecules, even though they're not rigidly bound to each other, they're closer together than they are in the case of solid water ice. So water actually expands as it freezes. And living in New England, this is something you probably should have some awareness of, because it gets cold in the winter, and if your water pipes in your house freeze, that means the water in the pipes expands as it freezes, and it might crack the pipe. And I guess that's not a problem as long as it stays frozen. But the problem is then when it warms up, cracked pipes tend not to hold liquid very well, and you could have a very, very big mess. This is probably quite useful for life, because if we're going to need a habitat where liquid water is available, if you've got a pond that gets cold where it freezes, starts freezing, then what's going to happen is, because solid water floats in cold liquid water, the ice is going to float to the top, and you're going to just freeze off the top, which will then kind of seal it, help insulate it, and make it harder to freeze all the way through. If instead you're trying to live in a cold pool of liquid methane that gets cold enough to freeze, solid methane is denser than liquid methane, and that methane ice is going to sink to the bottom, and your methane pool is going to freeze all the way through quite quickly, which won't happen as fast with liquid water. Now, it's also good that you've got to be able to dissolve some things, but not everything in water. So, for example, if the things that make up cell membranes dissolved in water, then cells would fall apart, and that wouldn't be good. But that's the good thing, is that water doesn't dissolve everything, and things like cell membranes stay together. Speaking of water, I'm recording this on September 18th, 2020, which happens to be the 150th anniversary of the discovery of the old faithful geyser in Yellowstone, or at least discovery by European American types. Presumably some of the people who were here before any Europeans probably had seen it before. So anyway, Old Faithful can be our attendance secret code for here. All right, the next video, which will conclude lecture 8, will be largely looking at starting to look at the organization of life on Earth, and in particular, in what's maybe the most fundamental unit of how terrestrial life is organized into cells. So, see you then.